I wish you a very warm welcome to this webinar. We're doing this on a monthly basis. It's the third webinar of this year. I will give you a small introduction of the company and the subject we are introducing to you this morning. The company is called SoMLabs. It's a Polish company established in 2003 approximately, specialized on systems on modules and carrier boards and single board computers. Maybe some practicals as usual also for these monthly webinars. We are running the webinar approximately for half an hour. In the meantime, I will watch the Q&A section. At the end of his technical presentation, I will take these questions one by one. In this way, he can focus clearly during half an hour on the content of his technical subject, and then at the last 15 minutes, we can cover the questions which are coming from the audience. I'm introducing to you our speaker for today, which is Krzysztof Chojnowski. He is a senior embedded software engineer at SoMLabs. He will give you an introduction to a Yocto project with SoMLabs. How does that work? What do you need to think about? What are the pros and the cons? Which are the tips and the tricks? He is specialized as a developer, and he's developing actually the microcontroller, and he works especially with the software layers. Krzysztof, the floor is yours.
Thank you very much. Good morning. My name is Krzysztof Chojnowski, and I'm pleased to tell you today a few words about Yocto in a practical way with some examples. So let's begin the presentation. So first of all, I would like to introduce you to basic concepts and structure of the Yocto project, what it is, and how can we use it in our products. I will give you some image of how can it be built and installed on the target platform. And I also include some examples about modifying, customizing the system distribution for our designed product. Today's webinar and today's example were created for Titan SBC 8M Mini platform. This is a single board computer designed and manufactured by SoMLabs. It is based on IMX 8M Mini processor made by NXP, and it's a platform that you can use as it is for your project. It has, of course, processor and the memories, and also commonly used interfaces like displays or communication like Ethernet, USB, etc. So you can use it as a development platform, or you can take it to your target application. We also use it during our trainings and webinars, so you may expect it also in our future meetings as well. So let's talk about Yocto. So first of all, people often use Yocto Linux name. It's not really precise. We of course know what does it mean, but Yocto is not a particular Linux distribution. This is more like framework and set of tools designed to build your own custom Linux distribution for embedded application. So it is, of course, open source framework that you can use for any hardware with provided software layers with support. Yocto is fully customizable for the designed application, so we can choose upon libraries, system tools or Linux managers that you want to include in the final system image, and everything is built from source code. So you always have the access to the source code. You can modify the source code of each and every library and software component. And finally, you always know what version of software is built and compiled together into one final single image that you get at the end. It is also cross-platform, so you can build it on any Linux desktop system that has appropriate tools and build the target system image. And it supports wide range of target hardware. So each main processor manufacturer provides Yocto support layer for their processor. In our offer, there are products with NXP, ST Microelectronics or Renesas processors, and each and every one of them has the Yocto support that is provided by the manufacturer and used by us to create demo and example systems for our modules and development board. So generally speaking, Yocto is a framework to build your Linux distribution with packages and system tools selected for the final application and final product. Sometimes we need to compare it to other solutions that are well known and commonly used on the embedded market. So I would like to add a few words to give you some picture of how it is related to another possible solution. So Debian related systems are well known from Raspberry Pi platforms. So if we take a look at this comparison, of course, there are some disadvantages of using Yocto because it may seem complicated at first look because you need to learn a lot of tools, project structure, the code of implementing receipts to create the particular software components, etc. You may not find the same packages as available in Debian releases, and you do not have access to pre-built packages repositories. In Debian system, whether it is desktop or it's Raspberry Pi or it's clone, you always have the Debian repositories where you can easily download and install software packages. We do not have such a convenient way to install packages in Yocto. In Yocto, everything is built from source. However, Yocto is optimized for the embedded systems and it contains only the packages that we need to. So the system is smaller, it's faster, and it is designed to use in particular application. It is not a generic distribution like Debian. And it also have support from manufacturers. Like I mentioned, each processor manufacturer provides Yocto application layer for their products. Debian is not really accessible this way. You often need to build the Debian release by yourself or buy it from some third-party company. Yocto sources are always provided for you to build your own distribution. And of course, Yocto is maybe fully customizable by you to use in a final application. So you may again decide what to include in the system. You are not forced to take everything that is provided with Debian image. And I would like also to compare it to Buildroot, which is, I think, the most commonly used project that is very similar to Yocto. It also builds the system distribution from scratch. Each component is built from source code. And also, it's in my opinion, Buildroot is much simpler than Yocto, which has more complicated structure, more configuration files, and more structured way to implement the compilation process. Buildroot is much simpler, and it's much easier to obtain minimal system image if you have some real strict requirements about storage. Buildroot may be better choice, and it is you can create the Buildroot system much simpler, much quicker. But on the other hand, Yocto gives you more flexibility. And also, in my opinion, it better supports multi-hardware configurations. You may create configuration files for multiple products, multiple hardware configurations, and build systems in a few configurations. So this is in Yocto is really great. And also it has a great ecosystem, which packages and software tools provided by different companies and communities. And I have impression that the scale of the ecosystem of Yocto is wider, and it's easier to find ready solutions to include in Yocto than in Buildroot. However, in this case, it also depends on experience and requirements for particular project to choose between Yocto and Buildroot. Both of them are frameworks designed to use in embedded systems. So now I would go more into details about Yocto project, about structure, and how to find the configurations and sources within the files provided. So if we download the Yocto project, for example, from SoMLabs repositories that we provide for our boards and modules, we will find a set of so-called meta layers. In the sources directory, the recipes, so the instructions to build every package is in one of the meta layers. The meta layer is related to the provider, like Meta Freescale, that contains the instructions to build the Freescale or NXP processor related components, some drivers, Linux kernel, bootloader for the product. We can also take a look at Meta Open Embedded, where we can find the Linux tools, for example, known from the desktop and distributions and commonly used Linux libraries, of course, open source tools. And we also provide our own meta layer, Meta SoMLabs, with the support for our own boards. So in those meta layer are the instructions to build the full system and each single component that will be included in the final software image. There is always a directory called Pokey. This is reference distribution, Linux distributions that is provided by Yocto Project. You can take a look at it and use the configuration files that are there and build your own distributions based on some parts of the provided reference. After we build the project and the system image, we can go into the build directory, where are all files from compilation or source codes and the build results like bootloader image, system image, the kernel and device tree files, everything that is a result of compilation process will be placed in the build directory. So this is the structure of the Yocto framework. And now let's take a look into one of the meta layers. Meta SoMLabs is a simple layer, so it acts as a nice reference of how is the structure, because each meta layer looks very similar. Of course, they have different packages and configuration files, but the structure of the directories and files remains the same. So we have configuration directory with a layer configuration file, which describes what is it and how it should be built together with other meta layers. We have also distro directory with distribution definitions, because each distribution that we create from the Yocto project has its own configuration files with the description of how this distribution should be created and what should be included in our image. And we have also machine directory with machine files. Each hardware platform that we built the Yocto project for has its own configuration file, like Titan SBC, as in our example, has also a configuration file describing the target hardware platform, the architecture and hardware components, and this configuration file is used later to create the distribution. And in each meta layer we find also recipes directories which contain software components. So, for example, recipes PSP is a directory that contains all the bootloaders and low-level software packages. We have also recipes kernel with the Linux itself, and also recipes SoMLabs in this meta layer with some application demos. In each meta layer we will find different recipes containing software packages, and each directory within the recipes directory contains some particular software component, like application, like a library or another Linux tool that is used in final image or during the build process. And here we have an example of SoMLabs demo recipe. In recipe SoMLabs directory, we have a SoMLabs demo directory with source code of our demo application. So first of all, we can see that there is a SoMLabs demo BB file. This is the recipe file. One of the Yocto tools is called BitBake, and it uses the BB files, like here SoMLabs demo.bb, to create the particular software component. So in the BB files, we have the full instruction of where to get source code, how to build, and how to install them on the target platform. So we can have the source code provided within the meta layer, like here. All the source files for the compilations are already in the meta layer, but we can also download them from FTP, from GitHub repository, or wherever we have the source code for our package. So in short, this is how the meta layers are organized. And the recipes, so the BB files, which are the core concept of Yocto project, they are similar in a way to source code of an application. So we can inherit some recipes classes or include some code or procedures that is defined in another BB files. So for example, we can have some commonly used compilation procedures that are used for Qt applications. So instead of implementing them by ourselves, so instead of writing the compile, configure, and install procedure, we can just inherit the Qt6 qmake recipe class to get all those procedures from another meta layer that implements it. We can also create our own recipe classes to not duplicate the code within the meta layers itself. So it resembles a little bit of a programming language. And also regarding the appending, we can extend the procedures that are contained within the recipes, but we need to tell the BitBake tool in which order, because each meta layer may have some extension. So each meta layer has also a priority value, which tells the BitBake tool in which order the meta layers should be aggregated and processed to avoid conflicts. So each meta layer has its own priority, like Meta SoMLabs has the priority 9. It's used at the later stage after all the lower priority meta layers are processed. Each recipe also looks very similar. So here we can take a look at more descriptive recipe file with some commonly used variables and procedures. So when we look into a BB file, we always find some header with description, license, and we can also add the inherit of the base class there. As I mentioned before, it's optional. We do not need to inherit anything. We may use some base class procedures. Then we need to define dependencies, if there are any, to tell BitBake and Yocto what needs to be built before our own package. If we need some other header files or libraries, we need to tell BitBake that something needs to be built before our own package. We also define the source location. It may be local or maybe at some remote GitHub repository, depends. We can also define the revision of particular code version and also provide checksum if we download something remotely to assure that everything is correct and the files are not damaged. And we also define where the source code are stored locally after download. Usually we have a workspace directory within the build directory, and there the source code is located and built by further procedures. And we also define the procedures for compilation, installation in our recipes. So these are the commands that are used to compile the application, install in the target file system. We can also have procedures to configure, patch, and everything we need to process our software into the final image. There are some commonly used and defined by BitBake procedure names, like do compile and do install here, but we can also define ours and place them between, for example, do compile and do install if we need additional steps of preparing the package. So this is how the general recipe looks like. You can find the similar variables and procedures in each and every BB file. So when you learn one of them, it's easier to get familiar with others software packages. Yocto is a huge project, so of course it needs good documentation, and we will find it almost everywhere in the web. The most important documentation sources are the manufacturer documents, like NXP, that provides documents for their processors. And we have also a general documentation for Yocto, where every variable, procedure, and mechanism within Yocto project is described, and are given also the examples of how to implement and change it in our own project. So these are the most important sources of the Yocto knowledge. We have also our own documentation as SoMLabs. You can find the instruction of how to build and install the example distribution for our development boards, like for the Titan SBC. You can go into the correct Yocto version, like Yocto ScartGap, which is the newest Yocto release right now on our Wiki pages, and you can find their link to their components like kernel and bootloader that are also on our GitHub, and the steps will take you through the whole compilation process. During this process, you will need also to select which hardware board you compile for, and which distribution you need. We have two distributions, one with the graphical environment, Xwayland, and one with the just terminal. So depending on your needs, you need to take correct board and the distribution. For our today's example, I prepared the distribution based on Titan SBC 8M mini configuration file, which is of course our development platform for today. And we also provide two example compilations with meta-IMX meta layer, or just with the community provided meta freescale. The difference between is that meta-IMX provides additional closed source drivers and examples by NXP company. The meta freescale is smaller. You can find only the crucial components to make your distribution smaller without additional software components. So depending on needs, again, you need to choose proper compilation command, and the compilation command the process is quite simple. When you have the local workspace directory, you need to initialize the repository itself. The repo init manages the GitHub repositories and downloads the Yocto sources that I described before. So all the sources with all meta layers are downloaded by repo init and repo sync procedures, and then you just select your chosen machine and distribution, and finally call the compilation command bitbake SoMLabs image, compiles the SoMLabs image system for the target board, together with the bootloader and all required software components. The bitbake with the image name takes usually a few hours of compilation time. After that, you get the final image to install on the target machine, and also bootloader that is required to program it into the eMMC memory. So everything is contained within the build directory, and you are ready to program the Titan SBC8M mini board. Everything is also described on our documentation page on Wiki, like on the link here. So you just need to connect the USB cable, micro USB cable to your PC. Here is also selected the small button on the back side of the board, which you need to press when powering up the board to let the processor go into the serial loader mode that allows you to communicate with the Universal Update Utility tool, shortly UUU, that is provided by NXP and is used to flash the boards with their processors. This is the way of how the Titan SBC port may be programmed with the system built by Yocto, according to the description. So now we'll go into the first development example. I would like to show you how a dev tool can be used to modify kernel image on the final system. So DevTool is one of the tools provided by Yocto, and it may be used for development and modification of source code of the packages built by BitBake itself. In this example, we will modify the Linux kernel, but you can do the same with any package that is within Yocto. So DevTool modify with the package name Linux IMX is the name of the kernel within the within our Yocto build. It downloads the source code, extracts it to some local directory where you can modify the Linux kernel. You can modify the configuration, the device tree, you can implement or modify the drivers, recompile, install to the target platform. For me, it's the easiest way to do some changes into the software component. The workspace that is created this way in the build directory, in the workspace subdirectory, is just another meta layer. Like the Meta SoMLabs, Meta Freescape workspace is one of them, is included into the build procedure of the BitBake. So when we have the sources extracted to the directory, we can, for example, add another drivers, like in this example. We can use the menu config tool. The menu config is a tool distributed with the Linux kernel. It's completely independent from Yocto. It's the graphical configurator for the Linux kernel. So if you call first the make devconfig, SoMLabs v8 devconfig is a base configuration for our boards of the Linux kernel, and then call make menu config, you will get a graphical configuration tool in your terminal when you can select the kernel components. Like here you can find, for example, sensors underscore LM75. This is the driver of the hardware monitor, the temperature monitor that has driver for kernel, and this way you can select it to be built together with the kernel. So this mechanism is completely independent from Yocto. It's just how we add a new components to the kernel itself. After adding it, you may save the configuration, like here, make save devconfig, and copy the created devconfig file to the SoMLabs v8 devconfig original devconfig file. This is crucial because SoMLabs v8 devconfig is the configuration file used for our processors. It's within the kernel recipe, kernel bb file, we defined to BitBake to use this file to configure kernel. So if you want the kernel configuration to change, you need to modify this file inside the kernel sources or provide your own and change the recipe. So here we modify the original devconfig file. Like here we can see that config sensors LM75 line was added to this file, and make mr proper is important because we modified the sources, and in order to build them properly, BitBake will need the sources to be clean. So we need to remove all the partial configuration files. So make mproper cleans the kernel directory from some temporary files. So to sum up the kernel modification, we also in the same directory may modify the Linux device tree, including the driver description that needs to be loaded by the kernel, like here in the I2C free section, we define what component hardware components added to the system and which driver the kernel should be used. How to create the device tree, we can find some help in the documentation provided with the kernel in the documentation directory, and the device tree file for Titan SBC is also listed here in the Titan SBC 8M mini DTS file. Okay. Finally, we can apply the changes to our meta layer. So if we add some commits to the repository which the kernel code resides in, we can create some local patches, and with the DevTool update receipt, like here, we can copy this patch to the meta layer. So our changes will be distributed to with our meta layer, so we won't need to modify them in external way. Just provide the patch for the kernel and distribute it with meta layer, and finally the patch itself will be located in the recipes kernel Linux IMX 001. This is the patch name, together with the bb files. bb append is the extension of the recipes. This added to the bb file. So in this example, we created modification patch to the original source code that may be distributed with the meta layer and modify the sources from the external repository. And this, I think, concludes this example. So to stay with the time agenda, I will also conclude the technical part. So thank you very much. And I guess this is the time to run the question and answer.
Thank you very much, Krzysztof. I will try. In the meantime, we have a number of questions, and I'm not sure if we can cover all of them during this webinar. Before I will start, I will pick, I think, the most relevant ones for the moment, just to offer to our customers the single board computer. We have a special offer for you together with our partner SoMLabs. €75, valid until the 31st of this month. If you want to order this sample, or you want to do some testing in some kind of project or beginning of project, feel free to contact us with that. Maybe to handle all questions, our field application engineer, Ibrahim, as said before, will contact you all individually. We have all your questions, your individual questions. So the ones I can try to cover together with Krzysztof today will be answered during the webinar. The ones we cannot really force into this 45-minute webinar, we will answer them offline, and you will get a dedicated connection with Ibrahim based on your question. So Krzysztof, the first question I am taking from the list is a question that came from Jasper. And Jasper is asking us, does your Yocto setup support RAUC for secure updates?
So our base distribution that we provide as sources on GitHub does not have any update framework included. I don't know about this particular framework, but I know that, for example, SW update framework can be included to Yocto build. There is also a framework called Mender. It's also quite easy to implement together with Yocto. So to answer it directly, I don't know about this particular tool, but the OTA tools exist to easy include them into Yocto build.
Okay, Dirk has asked another question saying, is there any existing support for migration from an older Yocto version to a newer Yocto version?
I guess regarding the application layer, that there is not a problem as long as the application works well with updated libraries like C library version. Regarding the hardware, you need to take a look at hardware configuration files. You need to take a look at, for example, changes in Yocto structure and commands that are available in the current version. So I think the best source is the changelog of Yocto, current Yocto project, to let you know how the structure is changed and how you need to change, for example, your recipes files. Because sometimes the procedures implementation needs to also change in the newer Yocto releases.
Okay. Another question from Jasper. How do you limit resources? And then he puts between brackets proc and mem used during built-in Linux for development.
I'm not sure if I understand how we limit resources. I guess we define the resources available in the target platform. I mean, the kernel and bootloader has the information about, for example, the memory availability and the particular processor, number of cores, etc. For the target image. During the building process, on the other hand, we can tell Yocto to use, for example, only part of our processors available on the development machine.
Okay.
If we do not use the 100% of our computer.
Okay. One last question, so we can more or less round off at 45 minutes. And as said before, the other questions will be taken offline through our application engineer, Ibrahim, together with you, Krzysztof.
Mm-hmm.
So we will reach out to the people who have put the question and we will answer them online or we'll contact you. The last one I'm taking is, what is the recommended host operating system to build the Yocto image, and which one is officially supported by Yocto?
Mm-hmm. So in the documentation provided by NXP, they suggest using Ubuntu operating systems, and they also list all the packages that need to be installed on the host system. And regarding the resources, there is actually, I don't think there is some minimal configuration. The thing is that the more resources we get, the shorter the compilation process will be. Regarding the disk space, I think at least 120, 150 gigabytes of storage is required, and the more cores we assign, of course, the faster the compilation process will be.
Okay, good. Krzysztof, thank you very much for
you.
Your interesting presentation. I wish you all a very nice day.
Thank you very much, and goodbye.